Now that we have run our regression model and we know that our equation is GPA is 1.22 times attendance minus 13.2, it's important to answer a certain question. Is this a good line? Does the line fit the data? This is a very important point because linear regression, when you perform linear regression and statistical software, what happens is that the statistical software will give you the best fit line. Now, this phrase is very important. Just because something is the best, it does not mean that it's good. If I do an exam and I get a 40 out of 100 on it, the grade is not good. Even if it was the best grade in the class, everyone else got less than 40, this does not mean that the grade is a good grade. So just because this is the best fit line, it does not mean that it is a good line. So we need a way in order to measure whether the line is a good fit or whether it does not fit the data properly. We do this by referring to something which is called R-squared. Now, in order to understand the concept of R-squared, let's use an example in which the relationship is actually not a good linear relationship. If we look at the scatter plot, we have y, the dependent variable, and x, the independent variable. If we feed the data that is shown in the scatter plot into a statistical software and we ask it to run linear regression, the statistical software is going to give us this output. This is the equation of a line. It is y is equal to ax plus b. We see that the slope is positive, so the line is sloping up, and we see that whenever x increases by 1, y is going to increase by 1. However, if you look at the scatter plot, I don't think that you can argue, or no one can argue actually, that the relationship between y and x is linear. It is not that it is a straight line where x and y are represented or have a common slope between them. So, although the data is not linear in nature, the data does not follow any line, any type of line. If you ask the statistical software to solve this for you, what the statistical software will do is that it will give you the line. It will give you the best fit line. However, although this is the best fit line, it is not a good line because the relationship actually is not a linear relationship. Therefore, we rely on something which is called R-squared. And in order to understand R-squared, we need to understand what does it measure. What we are actually trying to do is that we're actually trying to explain how the dependent variable or why the dependent variable takes on certain values. Some students have a high GPA, some students have a low GPA, other students have an average GPA. What we're actually trying to do is that we're trying to see whether the variable, the independent variable attendance, explains this variation in GPA. Whether attendance tells us why some students have a high GPA and other students have a low GPA. So R-squared is basically a measure of how much of this variation does our line actually explain. And the equation of R-squared is the following. It is the variation of the dependent variable that is explained by our line divided by the actual observed variation in the dependent variable. So basically in our data set, GPA is varying from the lowest value to the highest value, from student to student. And our line hopefully should try to explain this variation. The more that the line explains the variation, the closer that the value of R-squared will be to 1. Because in the ideal case, our line will explain all of the variation of the dependent variable. So basically we would be dividing the overall variation by the overall variation. We would get a 1. In the worst case scenario, our line will fail to explain any variation. So the numerator will be 0. 0 divided by the observed variation will be 0. This is why R-squared is in the range of 0 to 1. The closer it is to 1 means that the better the job that our line is doing in explaining the variation which we observe. So R-squared is a measure of the proportion of the variation that we observe in the dependent variable that is actually explained by our line. The higher the proportion of the variation that our line explains, the better our line. A good fit line has an R-squared value that is closer to 1, and a bad fit line has an R-squared value that is closer to 0. If we feed this into a statistical software and we calculate the R-squared value, what we are going to actually see is that the R-squared value is going to be somewhere around 0.0005, which is very low actually. And as we said, the closer it is to 0, the worse fit the line is going to be. If, however, we go back and we calculate, if we go back and we calculate the R-squared value for this data set that we have solved, what we're actually going to see is that the R-squared value for this model is 0.75. 0.75 is much closer to 1 than it is to 0. So this actually indicates that our line is explaining around 75% of the observed variation, and this would indicate that the line is actually a good fit line.